Good morning to everyone. I am Dr. REKA. Now I am going to talk about linear programming formulation in operation research. A linear programming problem deals with determining optimal allocations of limited resources to meet given objectives. The resources may be in the form of men, raw materials, market demand, money, and machines, etc. The objective is usually maximizing profit, minimizing total cost, and maximizing utility, etc. There are certain restrictions on the total amount of each resource available and on the quantity or quality of each product made. The linear programming problem deals with the optimization of a function of decision variables known as objective functions. Decision variables it is nothing but the variables whose values determine the solution of a problem are called decision variables of the problem, which is also known as objective function. Subject to a set of simultaneous linear equations known as constraints. The term linear means that all the variables occurring in the objective function and the constraints are of the first degree in the problems under consideration. And the term programming means the process of determining a particular course of a action. Linear programming techniques are used in many industrial and economic problems. They are applied in product mix, blending, diet, transportation, and assignment problems. And also oil refineries, airlines, railways, textile, textile industries, chemical industries, steel industries, food processing industries, and defense establishments are also the uses of this techniques. Next one, the requirements for employing linear programming problem techniques are follows. It must be a well-defined objective function, and it must be alternative course of action to choose, and at least some of the resources must be in limited supply, which give rise to constraints. Both the objective function and constraints must be linear equations or inequalities. Then the mathematical formulation of linear programming problem is as follows. If xj, that is here j equal to 1, 2, etc. n are the n decision variables of the problem, and if the system is subject to m constraints, the general mathematical model can be written in the following form, that is optimize z is equal to f of x1 comma x2 etc xn subject to the constraints gi of x1 x2 etc xn, which is less than or equal to or greater than or equal to bi. Here I is equal to 1 to etc m, and x1 comma x2 etc xn, which is greater than or equal to 0, which is called the non-negativity restrictions or constraints, and also subject to the constraints is called structural constraints. Next one, procedure for forming a linear programming problem model is, first step is identify the unknown decision variable to be determined symbol to them, and second one is identify all the restrictions or constraints in the problem and express them as linear equation of decision variables, and the next one identify the objective or aim and represent it also as a linear function of decision variables. Express the complete formulation of linear programming as a general mathematical model. We consider only those situations where this will help the reader to put proper inequalities in the formulation. Usage of manpower, time, raw materials, etc. are always less than or equal to the availability of manpower, time, raw materials, etc. The production is always greater than or equal to the requirements so as to meet the demand. This is the basic assumptions of linear programming problem. First one is proportionality. The contribution of any decision variables to the objective function is proportional to its value. For example, in the diet problem, the contribution to the cost of the diet from 1 pound of apple is $0.75, from 2 pounds of apple is $1.50, and from 4 pounds the contribution is $3.00. For 400 pounds, the contribution would be $300. In many situations, you might get a volume discount such that the price per pound goes down if you purchase more apples. These discounts are often non-linear. Watch that linear programming model is either inappropriate or is really an approximation of the real world problem. Next one, additivity. The contribution to the objective function for any variable is independent of the other decision variables. For example, in the energy production problem, the production of P2 tons of steel in month 2 will always contribute $4,000 P2 regardless of how much steel is produced in month 1. The proportionality and additivity are also implied by the linear constraints. In the diet problem, you can obtain 40 milligram of protein for each gallon of milk you drink. It is unlikely, however, that you would actually obtain 400 milligrams of protein by drinking 100 gallons of milk. Also, it may be the case due to chemical reaction, you might obtain less than 70 milligrams of um, by vitamin A by combining a pound of cheese with a pound of apples. Thus, the linear programming model is really just an approximation of what really happens. Next one, divisibility. Since we are using continuous variables, the linear programming model assumes that the decision variables can take on fractional variables. Thus, we got a solution to the GT railroad problem that sends 0. 0.7 locomotives from Centerville to Fine Place. In many situations, the LP is being used on large enough scale that one can draw the optimal decision variables up or down to the nearest integer and get an answer that is reasonably close to the optimal integer solution. For example, if an LP, that is linear programming for a production plan, set to produce 12,208.4 records, we can probably produce 12,209 and be close to an optimal solution. The problem in which some or all the variables must be integers or generally speaking much hard to solve than linear programming solutions. The divisibility also implies that the decision variables can take on the full range of real values. For examples, in the tennis problem, the linear programming may tell you bet $19.123567 on player A to win the match. Again, most of the problems we will encounter in this course are on a large enough scale that some rounding or truncating of the optimal linear programming decision variables will not greatly affect the solution. Next one is certainty. The linear programming model assumes that all the constant terms, objective function, and constraints coefficients as well as the right hand sides are known with absolute certainty and will not change. If the values of these quantities are known with certainty, for example, the demand data given in the NSC may be forecast that might not be 100% accurate, then this assumption is violated. So this is my reference. Thank you. Thank you everyone.